Let's do a problem involving springs. So this first problem, we have a 25-gram mass attached to a spring. The spring is stretched 15 centimeters beyond its normal length. Normal length refers to the equilibrium, or the center, basically, of the oscillation. The velocity as the mass passes the normal length is 45 centimeters per second. What is the value of Ks for the spring? What is the initial acceleration of the mass? And write the equations for distance, velocity, and acceleration of the mass. So let's take a look at what we're given. And the first is we have the mass of the object, and that's equal to 25 grams, or that's 0.025 kilograms. We have the amplitude. It says it's stretched 15 centimeters beyond the length. So we have the amplitude is 15 centimeters, and that's 0.15 meters. And it tells us that the velocity as it passes through the normal length is 45 centimeters per second. And remember, when we watched the video, the little simulation, we said that the velocity was a maximum when it passed the length. So we have the max velocity is equal to 45 centimeters per second, and that's equal to 0.45 meters per second. So these are the relationships that we have. Now, as we already said, the velocity is a max when it goes through that center point, and we know that max velocity is equal to the amplitude times the square root K of the spring over the mass. And this is what I'm looking for. I want K of the spring, so I can take and square both sides. And now if I simplify, I'm going to get K of the spring. Actually, I want to write it a little bit over so I have room to fill in everything. So the K of the spring is equal to the mass times the velocity max over A, and that's going to be squared. Now we have the mass is 0.025 kilograms, and we have the velocity 0.45 meters per second over 0.15 meters. Well, the meters are going to cancel, and that's going to leave me with, or if this is squared here, that's going to leave me with kilograms per second squared. and that will then relate to newtons per meter. Okay, so you do this calculation, you find that, actually I should write an arrow there, we find that the K of the spring is 0.225 newtons per meter. Now that I have the K of the spring, I can find the acceleration, and it's going to be A max is equal to the K of the spring over the mass times the amplitude and this is just going to give me our meters per second squared, and we calculate this as 1.35 meters per second squared. And the other property that we need is omega, because we need that for the equations, and that's the square root of Ks of the spring over the mass and that's just going to be equal to 3, and the units for omega are per second. Don't use frequency for omega. I'm sorry, don't use hertz for omega. Hertz is the units for frequency. Per second is the units for omega. Very important that you remember that. Now we can write the equations. Start with x of t, and that's going to be equal to 15 centimeters times the cosine of 3 per second times t. And we don't have a phi here because the spring was moved out to the amplitude. That would make phi equal to 0. So that's our distance function. Our velocity function is negative, and we know that our max velocity is 45 centimeters per second. With a sine of 3 per second times t, and our acceleration is minus 135 centimeters per second squared cosine of 3 per second times time. And that finishes the problem.